So we're going to have to go on a slightly meandering path to connect the two. So the first thing that I want to talk about is this idea of interoperability. So question, how many of you guys took a picture today? Where did you actually put that picture? So when I take pictures, you know, they end up in many different places. They are on Twitter, Facebook, Google Photos, Snapchat, Dropbox, sometimes in a Picasa, iPhotos, my old laptop, my new laptop, my phone, my old phone. It's a total mess, right? It's a serious mess. We have all of these apps and services that are trying to capture our photos, and none of them actually work together. Do you guys remember in 2012 when Twitter actually stopped working with Instagram? So you used to be able to see your Instagram photos inline in Twitter, on Twitter cards. And in 2012, Instagram decided that they wanted to capture your attention and your views, and so they made it so Twitter couldn't show those pictures. Now, I just want you to think about that for a second. This is a picture I took on my phone. I want to put it on my Twitter, and I could do that just by saving it to my hard drive and then uploading it to Twitter again. But instead of making it easy to do that, Instagram decided that they wanted to control that part of my data. They own the data, right? I don't own my own data. We have these things like fake interoperability everywhere. Like most apps have a share to Facebook or a post to Twitter link, but when it really comes down to it, you can't take your data out of the app, and you can't use multiple apps to act on the same data. And if you're a developer and you're writing one of these things, you know, maybe there's an API, but you end up having to write n squared different programs to connect n different services. So this is a lack of interoperability, and this is what I mean when I'm talking about data silos. Okay, I want to dig into another data nightmare that a lot of people have probably experienced. So how many of you have seen shelves like these? Maybe at your doctor? So these are medical records. They're medical charts. They hold really important data. Things like my weight, blood pressure, what vaccines I've had, what medication I'm on, what kind of treatment I have, like really important stuff that could mean the difference between life and death. My mother is actually a pediatrician, and when I would go to her office, I would see shelves just like full of this, like full of these charts. And at the end of the day, after she had seen her patients, she would come back to a pile of charts and she would start filling them out by hand based on who she'd seen that day. I don't know if you guys actually have these in Europe right now. This might resonate more with Americans, but you know, file folders are quite archaic. This is 2016. We could probably go digital. You can put health records in a database, and there's a name for this actually. It's called EMR, Electronic Medical Records, and it's a huge thing right now in healthcare. It's a massive, massive thing. A lot of doctors and a lot of practices are switching over to EMR, and there's incentives, like government incentives to do so. Unfortunately, going digital doesn't necessarily fix all of our problems. So how many of you guys have ever changed doctors? So did it just work seamlessly? Were you just able to like push a button and boom, you were at a different doctor and they had all your data? No, right? It was a disaster. And I don't think that this is just the case in countries without single-payer healthcare. You can imagine the same thing happening if you move across country borders, right? Changing doctors is still a mess. So when I did it, I had to go pick up my chart. I had to get a DVD with all of my x-rays on them, and I had to actually just tell my doctor some of my own medical history, like from memory, which is a terrible, terrible idea. So oftentimes the data, even if it's electronic and in a database somewhere, isn't actually transferable. So why is that? Well, when people build applications today, they kind of build them like this, okay? So this is like a pretty simple drawing. You've got this piece right here, which is the database. Databases are critical to most applications. They sit in the center managing state, and usually they fit a certain pattern. Before they were these really large, powerful, beefy servers. Now they're maybe more distributed or replicated. And then the application kind of sits on top. It's this cloudy sort of thing, writing back and forth to the database. And usually what we do is we hide our application or database behind this like thick red line, which is the network security perimeter. So the goal of this is to protect user data, which is totally fair, right? Companies need to be able to protect their data from malicious hackers. But unfortunately, this design has a lot of drawbacks. So sharing data, even within an organization, is really hard without giving others access to all of the data. And it's really hard to construct an audit trail. So if a problem happens, there's no way to automatically know who is the last person to access something. And a database administrator might have enough power to just change things without any sort of repercussions. Most importantly, this design discourages distinct applications from working together. It makes it super hard for applications across administrative domains to interact. For applications to compute on the same data, we need to do the following. As a user, actually go back and forth between the two applications and copy the data. Or we need to poke holes through our network security perimeters and set up an application programming interface, an API. And so what this means is that with two applications, there's at least two logical copies of the data. There's at least two logical copies of the data in two different schemas that were constructed after going through two different applications. And so each application often needs to do this manual reconciliation work, or you need to do it as a user to make sure that they have kind of the right data on each side. The worst part is that oftentimes, hold on a second, guys. I'm really sorry about this. I'm going to restart the talk. I think this is an old version, and I have a newer version, and I don't want to. Let's just go ahead and. PowerPoint crashed earlier, and so. Let's see what we got here. There we go. This is the right version. Cool. Okay, thanks for bearing with me. So we were just talking about how these applications have to do a lot of work to manually reconcile. And in my new job, we actually talked to a lot of different financial firms and banks and things like that. And they actually still send faxes. So faxes, FTP, and email is the way that these applications actually reconcile their data. The worst part is that, like I said, adding another provider means doing a whole nother integration with everyone. You have to do this manual back office reconciliation, and worst of all, compromises still happen. Data breaches happen all the time. So the whole reason that we were trying to set up this really like thin pipe outside of our network security perimeter was to protect our data. And it turns out that once a hacker breaches that network security perimeter, they're in and they have access to everything. So I think I see the beginning of a solution to this problem, and it's this new trend, and I'm calling it inside-out computing because it's fun to make up new names. So instead of this traditional picture, I think that things should start to look like this. We put the data and the validation first into a protocol. So using the abstraction of an append-only log with some relatively simple cryptography, we can have different applications actually act on the same data together. And what does this mean? It means it's really easy to add a third application if you want to. They just need to start speaking the same protocol. And a user can even go over the data and get access to it and do whatever they want with it. Maybe give that data to someone else. So there's a few really important pieces that are part of this, which I'm going to talk about now. Distributed consensus, public key cryptography, and common data formats and protocols. So first, let's talk about consensus. So consensus is this problem where you have many different computers that are trying to work together to agree on a value. It's used to build a log of operations with state machine replication, and oftentimes, if you set it up right, you can actually use this like a distributed database. Now, state machine replication is pretty simple. It's this idea that if everybody starts out with the same state and they follow the same set of deterministic instructions, they're going to end up with the same state. And this is what lets us use replicas and to replicate operations instead of actually replicating reads and writes. So distributed consensus operates under the fault tolerance model, and there are a lot of existing systems that do this. You probably use one of them at your company, Paxos, Zookeeper, Raft. It's this process of multiple computers all agreeing on a log of operations in the presence of faults. So even if a few of these servers end up failing, we're going to be okay. We're going to be able to continue in the presence of failures and construct this log. Now, you might not have heard of this other fault tolerance model called Byzantine fault tolerance. Now, in this model, things have gotten a little bit trickier, okay? So it's the same as before, except nodes might not just fail, they might be evil. So you might have heard this formulated as the Byzantine generals problem. And that's the idea that there are a bunch of generals who are trying to attack a city. And they're only going to succeed if they're able to attack at the same time, if enough of them attack at the same time. Now, the generals can send messengers back and forth to each other, but there's no guarantee that those messengers are going to make it. They might get picked off. And worst of all, some of the generals are actively turncoats and are trying to thwart the attack. And so Byzantine fault-tolerant protocols are this idea of being able to handle a few evil nodes and still come to consensus. This provides us with a very, very important primitive. It lets multiple distrusting actors work together to construct a single log. Now, this is an extremely old field. And here's a timeline. It was actually first talked about in the late 70s, early 1980s. Now, regular fault-tolerant consensus we hear about a lot. Like I mentioned, Raft and Zookeeper and Paxos. But we don't hear about Byzantine fault-tolerant consensus that often. It was really popular in the early 2000s in academia, and then it just kind of petered out. It sort of died off for a bit. But new systems, like Bitcoin, actually have a very related kind of model and are bringing back this really old field of research. So we have this log, right? We have these multiple different distrusting actors working together to create a log of data. But one thing we can actually do that's really helpful is we can add in these cryptography primitives. So with cryptography, the really important parts are asymmetric signatures and cryptographic hash functions. And so what this does is this lets us move security from around the data to within the data. We essentially have embedded security. So for example, if people encrypt the data that they put in this log and they keep the keys and the keys aren't leaked, then we don't need to worry about the log being public because no one else can see the data. Also, we can use signatures to be able to prove provenance and for users to port their identity across different providers. Instead of creating user logins per providers, we can use public-private key pairs. So that's great. A protected, encrypted log is wonderful, but we really want interoperability, and that doesn't happen if people can't use each other's data formats. And so a third critical piece of this picture is a format for records. What's important here is to put this agreement up front when designing the protocol, when designing the consensus protocol. And this is not a trivial thing, okay? This is standard setting. It is really, really hard to get a whole bunch of different actors, different companies together to agree on a standard. There are bodies like the W3C and the IETF that try to do this, and it's a really long, drawn-out, frustrating process. So I'm not saying that this is something that can just happen tomorrow, but I think it's really important. And by using this kind of a data model, you're putting that decision making up front so you can do it before you start collecting data and you don't end up having to reconcile two different data schemas. Okay. So what have we got here? This combination of distributed consensus, public key cryptography, and common data formats is really powerful. If we combine these things, we can get a system that can support interoperability, and we can have this totally auditable log, this log that uses signatures. And so what we can do is we can actually everyone can look at this log and sort of validate the signatures, check and make sure it hasn't been tampered with, and sort of make sure that the data is what they think it should be. And what I've just described is what we mean when we're talking about a blockchain. So how many of you guys have heard of the term blockchain? Okay, it's becoming very popular. And usually it describes the Bitcoin blockchain, though a lot of people are getting very excited about using this concept of a blockchain without Bitcoin, the currency. And really what this concept is it's these very old ideas that I just described to you presented in a new way. And part of what's going on here is that people are getting really excited about this idea of a global database in the sky that everyone runs but no one owns. Okay, so now I want to talk about how to use this log to build a decentralized digital currency. So we've got this log, and we've got cryptographic primitives. Now we've got to talk about how to actually build a digital currency on top of this log. Maybe the log is full of statements like this. So here's a transaction. It says, I, Alice, would like to send Bob 1 coin. Let's ignore where coins come from for now. Let's assume that someone else sent Alice a coin like this, and that Alice is just spending that coin again. So the log is just statements like this, people transferring coins to each other. But a problem here is we're operating in this decentralized environment, right? And so there could be attackers. Maybe there's this attacker, Mallory, and she actually wants this coin for herself. So she's going to steal it. She's going to try to steal it before it gets to Bob. Well, you know, Bob can say, hey, I know how to solve this. I have a public key, and I will tell Alice what my public key is, and she can include that in the transaction so that everyone knows when they look at the log that actually this coin is for Bob, it's not for Mallory. Well, maybe Mallory, she can't get that coin from Bob, but she really doesn't like Alice, and so she really would like to make Alice have some problems, right? And so maybe she wants to take this coin and spend it to herself. Well, Alice has a private key, and so Alice can just create a signature. She can sign the transaction, and by signing the transaction, she proves that it comes from her. And so she'll only sign transactions she wants to sign. And so Mallory is thwarted again. But maybe Bob is actually malicious, and maybe Bob thinks, great, I have this thing in the log that says I get a coin and Alice has signed it. Well, maybe I'll just replicate that and I'll give myself another coin. And this is called the replay attack. And so this is a pretty common attack in cryptocurrencies. And the way you get around it is you look at what got to the log first. So I want to make that really clear. This log is really critical to making sure that this cryptocurrency works. Another problem is that Alice could be evil too, and she could try to pay Bob and Carol with the same coin. So we're operating in a distributed system here, which means that you know, she could create these 2 transactions, give one to Bob and one to Carol, and say, hey, look, I paid you each a coin, so each of you should give me whatever I paid for. This is known as the double spend problem. And again, we need this log, we need this ordering of transactions so we know who Alice actually gave that coin to first. Now, the way these 2 problems, the replay attack and the double spend problem, used to be solved in digital cash was you used a trusted bank. So there was some third-party trusted bank that was in charge of making sure that these coins were used correctly. But we're trying to build a decentralized cryptocurrency. And so our motto is not to trust, but to verify. And I'm going to talk about how one of the most common cryptocurrencies out there, Bitcoin, actually does this and operates without a central bank. So let's say we have 4 transactions, okay? A, B, C, and D. Bitcoin uses this data structure called a Merkle tree, which is really cool. And what a Merkle tree is it's a very efficient way of proving that your data is contained inside of this overall tree. So you take these 4 transactions and you hash them. You compute these like small hashes. Then you compute another level of hashes. You take those hashes, concatenate them, and hash that. And you do this up to the root. And so this root is called a Merkle root. And it's a very small thing. You could have a massive tree with millions of transactions in it, and the Merkle root would still be the same size. And it would be this really cool combination of all of the things that are in the tree. And so what can happen here is that if I'm a client and I have a copy of the Merkle root, I can get the server to prove to me that my transaction was included in this tree in the following way. I have C. I'm trying to prove that C is in the tree represented by this Merkle root, and I have a copy of the Merkle root. And so I can take the hash of C. I can ask the server for the hash of D, and then I can compute the hash of those 2 things together. Then I ask the server for the hash on the left-hand side, which is A and B, and then I can compute the hash of those 2 things and make sure that it matches my Merkle root. And if it does, then I can be fairly assured that actually C is included in the server's tree. It would be very, very hard for the server to compute a different version of the left-hand side of the tree that would produce the same hash as if C wasn't in there. And Merkle trees exist for efficiency and for validation. You use them to prove to yourself that the server actually has the data that you think it does in the order that it claims to have it. And also, you do it without having to download all of the data yourself. Okay, so now we're going to use this data structure, a Merkle tree, and our log to help make this cryptocurrency. So I said before that this log was this list of transactions. We're spending a coin. Alice is giving Bob a coin. Bob is giving Carol a coin. So we've got this list of transactions, and that essentially is our currency. So maybe we're going to combine those transactions together in batches, so we don't have to, run a round of our protocol for every single transaction. And maybe we're just going to agree on all the transactions in a batch. Okay, great. So we have the transactions. We put them into this Merkle tree, and we get the Merkle root. And then we chain it to the end of the log. We add in a pointer to the previous block in the log, and maybe a timestamp for good measure. And when we compute the next block, we include a pointer to this block. And that's our log, essentially, and that's our currency. Our currency is this log of transactions constructed in the following way. So making this log, unfortunately, isn't as simple as taking existing Byzantine fault-tolerant algorithms that have existed for 30 years, because the problem with the existing BFT algorithms is that they require the participants to be known ahead of time. And so what that means is that we need someone doing admissions control. We need someone to bless the participants and assign IDs and let them into the system. But we're supposed to be operating in a trustless environment, so who controls admissions? Well, if we don't want to have anyone control admissions, then the attacker could just flood the system and outnumber the good guys, and then these protocols don't provide any guarantees anymore. So this is where Bitcoin's really novel innovation comes in, and it's called proof of work. It's known as mining, for those of you who are familiar with the Bitcoin protocol. Another name for it is actually Nakamoto consensus, because it's a consensus protocol. So Satoshi Nakamoto is this super shadowy person/group of people who put out this paper on Bitcoin in 2009 and then just disappeared. And no one knows who he is, and various news organizations will claim to have found Satoshi Nakamoto every 18 months or so, and they're usually wrong. It's actually, it's possible for someone to prove it. Satoshi Nakamoto has a set of keys, and if he were to sign something with his private key, it would be pretty good evidence that we'd found him, but no one's actually managed to gather that so far. I don't think he's going to come out of hiding. Not even sure if he's still alive. But he's the one who put out this Bitcoin paper. And in the Bitcoin paper was this idea of solving a computational puzzle. So it adds a couple of things to our previous data structure of the block, this idea of a nonce and a difficulty. And so what's happening here is instead of just constructing these blocks by creating a Merkle tree of the transactions, you're actually solving a computational puzzle, which is the pre-image of a hash. And so what that means is that anyone who wants to produce a block has to expend computational power and energy going through different nonces, taking the SHA-256 hash of the block with those various nonces, and seeing if what you get is matches the difficulty level specified in the block. So because of Satoshi Nakamoto and this paper in 2009, we now have things like this. So this is a massive data center full of racks of ASICs, which are application-specific integrated circuits. This is special hardware that has been designed just to solve this computational puzzle. And there are massive data centers like this all over the world, and what they're doing is they're spending time and energy and computational power computing random SHA-256 hashes in an attempt to create blocks in the Bitcoin blockchain and win a reward. Supposedly, the Bitcoin network is actually using the same amount of energy as the entire country of Ireland. Now, I don't know if that's actually 100% true, because peer review in this area is very spotty. It's unclear what the exact answer is, but it's very clear that the amount of energy the Bitcoin network is using is pretty large. So why do people even bother? Why do people buy this special hardware, set up these massive data centers, get this energy just to solve this stupid cryptographic puzzle? And why do they bother following the rules of the protocol and actually making sure that coins are disseminated the way that they should be? Well, it's the answer to most things in life. It's for money. So in addition to these three key parts that I said were part of interoperability, we need to add another very important component to enable open access, and that's called mechanism design. So in the field of game theory, and it's a field I don't know very much about yet, but there's this part of it called mechanism design. And in mechanism design, you have this goal or outcome that you want to achieve. And then what you do is you design a game such that if people play that game rationally, then it'll achieve your desired goal or outcome. So advertising auctions are an example of this. The way that they design the rules for bidding is to maximize the profit for the company conducting the auction. So in mechanism design, the end goal is known, but the game is not. You have to come up with the game. And this is a really key piece to design a system without trust, and this is what the Bitcoin paper in 2009 did. It presented a game with Bitcoin mining that if you played the game and you tried to make money and you tried to maximize your reward, then you would actually end up constructing a correct log of these transactions. So if you behave rationally when you're participating in the Bitcoin game, you'll try to solve this puzzle for Bitcoins, and because you're trying to solve this puzzle for Bitcoins and you're trying to get these Bitcoins, you're gonna play your game by building on the longest valid log you've seen. Now, there's a few key words here. The first one is longest. And so because you're building on the longest chain, you're building on the one that the other rational ones are building on. You're all working together. There's this idea in Bitcoin that you're going to build on the thing that you think everybody else is going to do so that when you win a block reward, your Bitcoins are valid. Another key word here is valid. So if you're following the rules of the protocol, then if you see a transaction that's invalid, for example, Alice trying to spend the same coin twice, then you're supposed to ignore it. So the incentive here is for people to build on the longest valid chain. Now, there's a big assumption here, which is that Bitcoins are actually worth something. If they weren't, why would anyone play this game? And why would we assume that these random digital strings are actually worth anything? Well, that's a whole nother talk. It's about money and economic value and how humans actually come together as a society and decide what has value and what doesn't. But the point is, Bitcoins can currently be exchanged at a rate of 1 Bitcoin for about $440 USD right now. So we can apply the game theory. And when miners mine a block right now, they get a reward of 25 Bitcoins. So it's worth it for them to try to play this game, solve the computational puzzle, and produce a correct version of the log. So we've made a slight change to the traditional Byzantine fault-tolerant consensus model, the one that's 30 years old. So before we had this, we had evil guys and we had good guys, and as long as there were only a few evil guys, we knew we could make progress and we knew that we could compute this log correctly. But now we're in a totally different model, where instead of having evil guys and good guys, it's just mostly independent, rational actors who are participating. And as long as most of them don't collude, which actually seems to happen in practice, then there will be one longest chain which only contains valid transactions. And so the reason for that is because even if a few of them try to collude to include a block that's not valid, eventually, because most of the hash power is trying to do the right thing, they'll end up creating a longer version of the chain. And that will be the true version of history. Now, there are a lot of downsides to Bitcoin. So one thing is the energy usage of proof of work, which is required to secure the system. It's there to provide this rational incentive, but it is quite large, the amount of energy that this system consumes. Just to sort of as a side note, a lot of the energy that goes into the system comes from places where they have a lot of hydroelectric power or wind power or solar power, and they're actually able to get this energy really, really cheap. So, and the energy would literally just be going to waste if it wasn't used for this, so it's not like a total horrible thing for climate change. This energy would be there anyway. Another problem with Bitcoin is performance. We have thousands of nodes working together to perform this consensus algorithm, and it's pretty costly. You guys might have heard about the scalability debate that's happening in the Bitcoin community right now. It's been over a year, and people still can't decide, number one, if they should scale the system, and number two, what the best way is to scale the system. Another big problem is concentration of mining power. So currently, the majority of the mining power is contained in China. And the question is whether or not that's okay. Bitcoin operates on the edges of legality, I would say, and it's really unclear how countries are going to respond to this currency in the future and as it grows bigger. Another big problem is its difficulty of use. How many people here have actually ever spent Bitcoins? Okay, a few of you. How many people found the process enjoyable? It's like, okay, it's a huge pain, basically. You have to generate these keys, you have to get a wallet, you have to do all these different things. It's not as easy as sticking your credit card into a machine or just typing in a number, unfortunately. And then a final downside of Bitcoin is the uncertainty of this new currency. It's really volatile. The price has a lot of swings, and therefore it's not really a great store of value or a great currency. It's not a great medium of exchange because the value is changing so often in comparison to other currencies. But I think there are a few things that we can learn from Bitcoin, actually, and that we can use in the next generation of systems that we build. So first of all, this idea of an open admissions, rationality-based, Byzantine fault-tolerant protocol at large scale is pretty groundbreaking. We've never had anything like this before. And I really think that it's going to be key to figuring out how to get people from different domains and different companies to operate on the same data together. Already, there are a lot of consortiums that are being used in the financial world. One is called R3, the other is Hyperledger, where some of the world's largest banks are coming together to try to figure out how to use this technology for financial transactions. Another thing we can learn is that simple, standardized transaction formats are actually incredibly useful. So the Bitcoin transaction is relatively simple. It only has a few parts, and people are building all kinds of crazy applications on top of it. It's not just for currency. And then the final thing is that giving users the power to audit and control their own transactions is really powerful and amazing. We should build more systems like this, where we put the data in the hands of the user, and we give them the ability to take it out and put it where they want. And so I just wanted to leave you with this idea that more open systems with less trust are going to end up meaning that we have more choice and more options and more interoperability. Because when there's no trust, there's no gatekeeper. There's no one who can keep out that next cool app that I want to use. They don't have to ask for permission. They can just plug in and start working immediately. Now, what's really surprising, and was surprising to me when I started working in this area, is that people see a lot of real-world applications here. Here are just some of the projects that my group at MIT is working on. There are some traditional ones that have to do with money, like savings and credit practices in the developing world, mobile money, real-time gross financial settlement. But then there's all these other things that I didn't really think had anything to do with Bitcoin and the blockchain, but people actually see a use here in this abstraction of a growing append-only log. Credentialing, so having a place to put user credentials that's not locked up inside of a company. Property titling and asset transfer. There was an article in The Economist about a year or two ago talking about how to potentially do property titling on a blockchain. Global rights management for music. Music contracting has been a mess, apparently, for a really long time. And so this is another area we're exploring. Medical records, like I talked about before. And decentralized publishing. So getting content out of the hands of sort of like blogging companies and places like Medium and sort of giving it back to the users. So I hope you learned a little bit about cryptocurrencies today. Maybe you got more interested, maybe you want to learn more. This is my contact information, and thank you all so much. Cool.
There are a few questions on Slido. We'll pull that up right now. The first one, there was a finite number of bitcoins. So once they run out, how will the blockchain continue to grow?
Great question. So it is true right now that most of the reward for computing a block, and thus, the reward in the game theory of actually doing this, comes from the creation of Bitcoins, the minting of new Bitcoins, which I didn't really talk about. And it is also true that that number, according to the protocol, is dropping over time and will go to 0. So what's supposed to rise are transaction fees. So not only do people who mine a block get a reward of Bitcoins for mining a block, but they also get to take any of the transaction fees. And there's an incentive for people to include transaction fees, because if they don't, their transactions won't get processed. So the idea is that over time, transaction fees will grow. And actually, pretty recently, I think someone accidentally created a transaction in which they put the transaction fee in the wrong place, and they gave a miner $135,000. So they paid a transaction fee of $135,000, which is crazy. But that's gone now. That just happened. Anyway, okay, so let's look at the next question. Okay, storing health data, although encrypted on a blockchain, seems dangerous. The data remains sensitive long-term, and crypto algorithms are proved insecure over time. I think that's absolutely true. The project that we have going on in this area doesn't actually store the records on a blockchain, and I think that really what we're looking at here is we're looking at different kinds of systems which might integrate a blockchain for just part of the system. We're storing permissions on a blockchain. So it's a place to go to see who has access to what, and who something has been shared with or not shared with. The project going on at MIT is called MedRec, and the data is actually still stored with the provider. So I totally agree with you. We have to be very careful when we're designing these systems. Can you comment on the usage of the various tools, platforms to implement applications on top of blockchain? Oh, that's a really good question. So there's a few different, there's two major cryptocurrencies out there. One is Bitcoin and the other is Ethereum. And there's different kinds of tooling available for each. I'm not super familiar with Ethereum. I know for Bitcoin there are libraries available in several different languages to add things to the Bitcoin blockchain, to manipulate data, to read from the blockchain. But this area is still pretty new. It's still pretty nascent. So I don't think the tooling is as developed as you might like it to be. And if you're using the Bitcoin blockchain directly, this is one thing that I didn't mention, but there is on the order of like tens of minutes for a confirmation time. It's not an instantaneous thing. It takes a while for a block to be mined with your transaction and for that to be confirmed. Okay, can you briefly explain the causes of the scalability issues in Bitcoin? Okay, sure. So this is a really interesting question. So this debate has been going on for over a year, and there were actually 2 conferences to try to help sort it out. And I went to the last one in Hong Kong, and we still don't really have a very good answer. The short answer is that I think that there are a lot of startups that have built their business model on the idea of fast, cheap payments, and that's what they want to use Bitcoin to do. And so their goal is to be able to process as many payments per second as possible, as cheaply as possible. And so that's what they're going for, and so they have a strong incentive to try to pack in more transactions. Right now, Bitcoin is designed not to scale. It is designed, like every parameter is set so that you can only do so many transactions per second. And it's not like an accident of the design, it's very much intentional. The idea being that, and this is like a little bit of a subtle argument, so you might not buy it, and that's totally fair. I think this area is pretty complex. But the idea is that we really, really, really want lots of people to be mining Bitcoin and running validation nodes, because the more people doing so, the more decentralized the network is. And if you make it really expensive to do that, and if you make it require a lot of resources like bandwidth and disk storage and CPU, then not so many people are going to do it. Only people who can afford to buy the machines and the networking access are going to be able to do it. And given that there's things like the Great Firewall of China, bandwidth is actually not so great between different parts of the Bitcoin network. And so you can't actually support that high of a bandwidth rate in moving these blocks around. And so there are a lot of people who want to really keep a lot of pressure to keep things like the block size low, and to keep the bandwidth and the disk storage and the CPU usage low, so that the network remains more decentralized. Let's see. Could the blockchain be used for verifying electronic voting? So that's a really interesting question. And there are a lot of people who are trying to build these sort of like decentralized voting apps. And another area that I didn't even talk about is this idea of decentralized autonomous corporations. So this is, if you want to read more about this, go read, there's a ton of blog posts in the Ethereum area about basically taking a program and putting it out there and just letting it run. And once you've written the program and sort of published it to a blockchain, it's then autonomous in some sense. No one can take it down. And so voting is like a really rich field, which is also another fascinating area of cryptography. I would say that people are looking into doing this. I don't think that it's the only solution or necessarily the right one, but it might be one. It's very exciting. Cool. Okay, thank you, everyone.